All right, let's dive right in. We're going to talk about one single element that is, and I mean this literally, the foundation for, well, everything, all of life, and so much of the world we've built. We are, of course, talking about carbon.
Okay, so let me start by asking you a question, kind of a riddle. What do you think connects a flawless diamond, the gas you put in your car, and the very cells that make up your body? What's the one common thread?
Yep, you got it. It's carbon. It really is the unsung hero of our entire world, right? The ultimate building block, the absolute element of life.
So, what's carbon's secret? What makes it so incredibly special? Well, to really get it, we've got to look at how it plays with others. It all comes down to how it forms bonds. You could almost say it's the most social, most friendly element on the entire periodic table.
And the magic number for carbon's social life? It's this one right here, 4. See, a carbon atom has these 4 electrons in its outer shell. They're called valence electrons. Just think of them as 4 hands, always ready to reach out and connect with other atoms.
So, how exactly does carbon make all these friends? It's not pushy. It doesn't just steal electrons from other atoms. Nope. Instead, it shares. It forms something called a covalent bond. The best way to picture it is like a really firm, friendly handshake. 2 atoms just agree to share their electrons. No drama, just partnership.
And remember those 4 hands we talked about? Well, because it has 4 electrons to share, it can make 4 of these super strong, super stable handshakes at the same time. This power, chemists call it tetravalency, is basically carbon's first superpower. It makes it the ultimate connector in the universe.
But wait, there's more. Connecting with other elements is one thing. What really sets carbon apart, what makes it a total game changer, is its ability to connect with itself. This leads us to its second superpower, building these long, incredible chains.
There's a fancy word for this, catenation. And you guys, this is the key. I mean, sure, other elements can link up a little bit, form some short chains, but nothing can do it like carbon. The length, the stability, it's in a league of its own. This one skill is the whole reason life is carbon-based. It's the only element that can build the long, complex backbones that life requires.
Now, not all of these carbon-carbon links are created equal. You can have single bonds, which create what we call saturated molecules. Think of these as calm, stable, and not looking for trouble. But you can also have double or even triple bonds. These create unsaturated molecules, and they're way more reactive, kind of itching for some chemical action.
Okay, so carbon has built this amazing backbone, this chain. This is where the real fun starts, because now you can start accessorizing that chain. You can attach these little clusters of other atoms, and we call them functional groups. And these little add-ons, they give the whole molecule its unique personality, its specific job.
Yeah, you can really think of them like charms on a charm bracelet. Each one tells a different story. So you snap on an OH group and boom, you've got an alcohol. Or you add a COOH group and now you've made a carboxylic acid. That's the stuff in vinegar. Just one tiny change, one different charm, and you've completely changed what the molecule is and what it does.
All right, so we've got our carbon chains, we've got our accessories, our functional groups. So what happens when we let these things loose? Let's see how they actually react with each other.
Well, one of the most common and, explosive reactions is combustion. That's just a sciencey word for burning. Anytime you burn something like natural gas, what you're really seeing is a carbon compound freaking out with oxygen. And the result? A huge release of energy, plus some carbon dioxide and water. I mean, it's the reaction that basically powers our entire world.
But it's not always so dramatic. Carbon compounds can do much more subtle things, too. Take substitution reactions. It's basically like a player getting subbed out in a game. One atom leaves, and another one tags in to take its place. Just like that, you can swap a hydrogen for a chlorine on a methane molecule. It just goes to show how flexible and modular these carbon structures really are.
Okay, time for the grand finale. Let's pull everything we've talked about together. The chains, the functional groups, the reactions, and use it to understand something you probably used this morning. We're going to talk about soap.
So, our little soap-making journey. It starts with a pretty basic alcohol. We're talking ethanol. Just a simple 2-carbon chain with an alcohol group on it.
Okay, ingredient number 2. We're going to add a carboxylic acid, specifically ethanoic acid, which you probably know is the main component of vinegar.
Now, when you mix these two together, a reaction called, get this, esterification happens, and you create a totally new kind of molecule, an ester. And the cool thing about esters? They smell amazing. Really pleasant, fruity smells. This is exactly where perfumes and artificial fruit flavorings come from.
Pretty cool, right? But now, what if we run that process in reverse? Well, there's a reaction for that too, called saponification. It literally breaks esters apart. And this is precisely how we make soap. You take a different kind of ester, think fats, like from vegetables or animals, react it with a base, and you end up with an alcohol and a carbon-based salt. That salt, that's your soap.
And this molecule is where the real magic is. Seriously, this thing has a total split personality. On one end, you have this long carbon tail that is hydrophobic. That means it hates water, but it absolutely loves oil and grease. Then on the other end, you have a hydrophilic head, and you guessed it, that part loves water.
So picture this. You're washing your hands. All those little soap molecules go to work. The oil-loving tails see a piece of dirt or grease and they dive right in, burying themselves deep inside it. Meanwhile, the water-loving heads all stay on the outside, pointing out towards the water. They form this tiny little cage, a sphere, called a micelle, with the dirt trapped right in the middle. Then, when you rinse, the water comes along, grabs onto all those water-loving heads and just whoosh! It washes the entire micelle away with the dirt trapped inside right down the drain.
So there you have it, from a simple little atom with 4 hands all the way to the complex chemistry that gets us clean. Carbon really is nature's ultimate Lego block, isn't it? Its power to build chains, to connect with everything, and to be customized with functional groups, that's not just cool chemistry, that's the very basis of life itself. Which leaves us with just one big question. What are we gonna build with it next?